Journey Through Time welcomes you to an extraordinary exploration of the Moon, our closest cosmic companion, and one of the most mysterious bodies in our solar system. Tonight, under the quiet glow of its silvery light, we invite you to journey far beyond familiar craters and shadows. Together, we will uncover hidden truths, strange phenomena, and ancient secrets locked in the lunar surface, mysteries that continue to intrigue scientists, astronomers, and dreamers alike. Sit back, relax, and allow your imagination to drift beyond Earth's sky as we begin our story of the Moon's most fascinating enigmas. For more than half a century, the Moon has been both a laboratory and a riddle for humanity. In November 1969, during the Apollo 12 mission, NASA did something unprecedented. After safely returning to the command module, astronauts deliberately crashed the lunar module's ascent stage onto the Moon's surface. This was not an accident, but a planned experiment designed to test seismometers left on the Moon during earlier landings. When the impact occurred, those instruments recorded something no one expected. Instead of a quick dampened tremor, the Moon vibrated for over 50 minutes, like a massive resonant bell struck by a hammer. The phrase, "The Moon rang like a bell," became an instant headline and sparked decades of speculation, research, and even conspiracy theories. On Earth, earthquakes dissipate energy quickly because our planet has a molten, dynamic interior that absorbs and scatters seismic waves. The Moon, by contrast, showed a totally different response. The vibrations propagated evenly and persisted far longer than scientists had ever observed in a planetary body. This suggested that the Moon's interior was dry, rigid, and perhaps far less geologically active than Earth's. Some people went further, suggesting that the Moon might even be hollow, an idea never supported by mainstream science, but considered briefly because the data was so unusual. Subsequent missions deepened the mystery. Apollo 13 never landed on the Moon, but contributed one of the most important data points to this story. In April 1970, NASA intentionally crashed the Saturn V upper stage, an empty rocket booster, into the lunar surface with the force of 11 tons of TNT. The Moon's seismometers once again recorded the event, and this time, the reverberations lasted more than 3 hours. Some frequencies continued for over 8 hours, behaving less like chaotic fracturing and more like a clean resonance. The implication was clear. The Moon's interior structure did not resemble the Earth's and might hold unexpected surprises. Modern data from NASA's Gravity Recovery and Interior Laboratory, GRAIL, mission paints a more nuanced picture. We now know that the Moon has a thin crust, averaging about 50 kilometers deep, a partially molten mantle with zones of different rigidity, and a small inner core surrounded by a liquid outer core. Crucially, the Moon's overall density is much lower than Earth's, and it is extremely dry. Without water or molten rock to absorb and scatter seismic vibrations, energy can bounce around inside for much longer, creating that eerie bell effect without requiring a hollow shell. Yet, despite updated models, the metaphor of a ringing moon has stuck, continuing to inspire curiosity and theories at the edge of science. The Moon's seismic mysteries are only one piece of a much larger puzzle about its origin and nature. For decades, scientists believed they had a solid explanation for how our satellite formed. The prevailing idea, called the giant impact hypothesis, proposes that over 4.5 billion years ago, a Mars-sized body, nicknamed Theia, collided with the young Earth. Debris from this cataclysm was hurled into orbit and gradually coalesced into the Moon. For a time, this model fit neatly with several key observations. The Moon's lack of a dense iron core, its relatively small size, and its distance from Earth all aligned with predictions from computer simulations of such an impact. However, when Apollo astronauts brought back hundreds of kilograms of lunar rock, a new problem emerged. Detailed analysis revealed that the Moon's chemical fingerprint, especially the ratios of oxygen isotopes, was almost identical to Earth's. According to the original impact model, the Moon should contain a mix of material from both Earth and Theia, resulting in a different isotopic signature. Instead, it appears to be made almost entirely of Earth-like material. Some scientists tried to patch the model by suggesting that Theia had a composition nearly identical to Earth's, or that the impact thoroughly mixed both bodies, erasing their differences. But these explanations raise their own questions. What are the odds that two separate planetary bodies formed in different parts of the solar system would be so chemically alike? And if they mixed so perfectly, why is the Moon's makeup still so much closer to Earth's mantle rather than a random blend? Other theories emerged to account for the data. The co-formation theory suggests Earth and Moon formed side by side from the same disk of material orbiting the Sun, which would explain their chemical similarity, but not their current orbital dynamics. The capture theory imagines the Moon forming elsewhere and being gravitationally trapped by Earth, a scenario that's mathematically improbable for an object so massive. More radical ideas propose multiple smaller impacts, or even a long, slow accumulation of material, rather than a single collision. Each alternative struggles with at least one key parameter: mass, angular momentum, or chemical composition. And no model fully explains the Moon we actually see. This persistent mismatch between theory and observation makes the Moon's origin one of the most debated topics in planetary science today. Complicating matters further are the Moon's unusual orbital characteristics. Its size relative to Earth is far larger than typical planet-Moon systems, and it's tidally locked, always showing the same face to our planet. Most intriguingly, its apparent size in our sky almost exactly matches that of the Sun, enabling perfect total solar eclipses, a rare and striking coincidence unique in the solar system. This alignment has inspired myths, scientific speculation, and even fringe theories about the Moon's placement, but it also underscores a deeper truth. Our satellite is not a mundane companion. It is an outlier, and outliers often hold the biggest secrets. If the Moon's composition and orbit weren't strange enough, its age raises even more profound questions. Radiometric dating of lunar rocks, particularly anorthosites from the highlands, shows ages of 4.4 to 4.5 billion years, only slightly younger than the solar system itself, and hundreds of millions of years older than Earth's oldest known crust. Some zircon crystals found in lunar samples even predate Earth's surface entirely. This suggests that parts of the Moon may have formed before the Earth's crust solidified, or that material from an even older planetary body became incorporated into the Moon during its creation. In either case, the Moon is not merely Earth's child, but a repository of pre-Earth history, a time capsule from an era otherwise erased by our planet's plate tectonics and erosion. This possibility reframes the Moon as more than just a companion in orbit. It becomes an archive of cosmic history. Earth's geology constantly recycles itself through subduction zones, volcanism, and erosion, erasing much of our earliest record. The Moon, lacking these processes, preserves its ancient surface almost untouched. Every crater, every mineral grain, tells a story of bombardments, magma oceans, and chemical processes dating back to the dawn of the solar system. By studying lunar samples and mapping its terrain, scientists gain access to a chapter of planetary evolution that's missing from Earth. Adding to this archive are bizarre features, like the Moon's sodium tail, a tenuous comet-like plume of atoms extending hundreds of thousands of kilometers into space and sweeping over Earth once a month. This tail, invisible to the naked eye, results from micrometeoroids striking the Moon's surface and knocking free sodium atoms, which are then pushed outward by sunlight. Each month, as the Moon passes between Earth and Sun, our planet actually moves through this ghostly stream, a silent reminder of our dynamic connection to our satellite. The Moon is not inert. It leaks, interacts with space, and responds to solar and cosmic forces in ways we're only beginning to measure. Taken together, the seismic ringing, the puzzling origin, the ancient rocks, and the invisible tail. These details transform our perception of the Moon from a static gray rock into a living scientific enigma. They hint at a deeper complexity beneath the surface and a richer backstory than our textbooks once imagined. For future explorers, every mission to the Moon is not just a journey outward, but also backward in time, touching fragments of worlds older than Earth and phenomena stranger than we dared to believe. The Moon's surface, though seemingly quiet, hides a world of hazards and phenomena that directly affect our plans for living there. One of the most important of these is moonquakes, real seismic events recorded by Apollo seismometers between 1969 and 1977. Over several years, those instruments detected thousands of quakes of varying strengths. Scientists classify them into 4 types, each revealing something about the Moon's inner workings. Deep moonquakes, occurring hundreds of kilometers below the surface, seem to be linked to tidal forces from Earth's gravity. These events happen regularly and demonstrate how the Earth-Moon system continuously exchanges energy. Shallow moonquakes, however, are the most concerning. Occurring just tens of kilometers beneath the crust, some have reached magnitudes of 5.5 on the Richter scale, powerful enough to rattle hypothetical lunar bases for many minutes at a time. Because the Moon's crust is rigid and dry, vibrations travel farther and last longer than on Earth, creating a prolonged shaking effect. In addition to these 2 types, there are thermal quakes, which occur when the lunar surface undergoes extreme temperature changes. With no atmosphere to moderate sunlight, the Moon's day can heat the ground to over 120 degrees Celsius, while nighttime temperatures plunge below 170 degrees Celsius. This expansion and contraction can create cracking sounds and minor quakes as the crust adjusts. Finally, there are impact-induced quakes, produced by meteoroids striking the surface at high speeds. Since the Moon lacks an atmosphere, even small space rocks hit with immense force, producing seismic waves that can travel long distances. Future habitats and infrastructure will need to account for all these sources of shaking, designing structures capable of absorbing or withstanding long-duration vibrations in an environment with no natural damping from soil or water. Perhaps most troubling, many of the recorded shallow quakes occurred near regions of high interest for exploration, including the lunar South Pole, where water ice may be hidden in permanently shadowed craters. These areas are attractive for long-term bases, but may also be seismically active. Scientists think that some of this activity could be remnants of the Moon's still cooling interior, or the result of crustal compression as the Moon slowly shrinks. In fact, recent analyses of Apollo data suggest newly discovered fault lines coincide with some recorded quakes, implying the Moon is still tectonically active, albeit on a subtle scale. This challenges the old assumption of a geologically dead Moon and raises questions about how stable its surface really is for human settlement. Beyond seismic surprises, the Moon holds another misunderstood feature: its so-called dark side. Popular culture, from music albums to science fiction films, has painted the far side of the moon as a place of eternal darkness, mystery, and secrecy. Yet in reality, the far side receives just as much sunlight as the near side. The term dark is a misnomer, dating back to the era when the far side had never been seen from Earth. Because the moon is tidally locked, it rotates on its axis once every 27.3 days, the same period it takes to orbit Earth, so we always see the same hemisphere. The far side only appeared dark to us because it was hidden from view, not because it lacked sunlight. When the Soviet Luna 3 spacecraft finally photographed the far side in 1959, it revealed a surface dramatically different from the one familiar to Earthbound observers. Instead of the dark basaltic plains, or Maria, that dominate the near side, the far side is heavily cratered highlands with far fewer lava flows. This asymmetry may be due to a thicker crust on the far side, preventing magma from reaching the surface billions of years ago, or to differences in heat distribution during the moon's formation, when Earth and Moon were still molten. Modern missions, including NASA's Lunar Reconnaissance Orbiter and China's Chang'e program, have mapped the far side in exquisite detail, turning mystery into data. In 2019, China's Chang'e 4 became the first mission to land on the far side, using a relay satellite to maintain contact with Earth and opening a new chapter in lunar exploration. Despite these advances, the mythology of the dark side persists because it resonates with human imagination. For centuries, the unseen hemisphere was a blank canvas for speculation about alien bases, hidden cities, or cosmic secrets. Today, scientists see it as an opportunity for radio astronomy, shielded from Earth's electromagnetic noise, and as a potential location for future scientific bases. In fact, the far side may hold some of the oldest and most pristine craters in the solar system, untouched by the volcanic resurfacing that reshaped the near side. Rather than a dark, forbidden realm, it is a scientific frontier, one that promises to teach us more about the moon's evolution and about the early history of the solar system than any other region. One of the moon's most astonishing recent revelations is the discovery of rust, real iron oxide, on its surface. For decades, textbooks taught that the moon was airless, waterless, and chemically inert, making rust formation impossible. Rust requires both oxygen and water to form, yet the moon seemed to lack both. Then, in 2020, researchers analyzing data from India's Chandrayaan-1 orbiter found spectral signatures of hematite, a form of rust, near the lunar poles. This was shocking. Where could the moon be getting the ingredients necessary for oxidation? The answer may lie in Earth itself. Our planet's magnetic field stretches far into space, creating a long magnetotail. During certain parts of the moon's orbit, especially around full moon, the moon passes through this magnetotail and becomes briefly shielded from the solar wind. At the same time, oxygen atoms from Earth's upper atmosphere drift outward along magnetic field lines and can reach the moon's surface. Even though the quantity of oxygen is minuscule, over millions of years, it could react with trace amounts of water, bound in lunar minerals, slowly creating rust. This process is counterintuitive, but reveals a hidden connection between Earth and Moon, one that goes beyond gravity, a chemical bridge spanning hundreds of thousands of kilometers. Adding to this picture is the growing evidence that the Moon does, in fact, hold water in various forms. Tiny glass beads in Apollo samples contain molecular water, hinting that the Moon's interior once harbored water-rich magma. Permanently shadowed craters at the lunar poles are cold enough to trap and preserve ice delivered by comets and asteroids over billions of years. In 2009, NASA's L-Cross mission deliberately impacted a crater near the South Pole and detected a plume of water vapor and ice particles. And more recently, instruments have confirmed hydroxyl molecules spread across the sunlit surface. Together, these findings overturn the old assumption of a bone-dry moon and show that it is more chemically active and more intricately tied to Earth than we ever suspected. While rust and water hint at subtle surface chemistry, the moon may also conceal something far more dramatic underground. Massive lava tubes, potentially kilometers wide and extending for many miles. Billions of years ago, the moon was volcanically active, with molten rock flooding across the surface to form the dark plains we now call Maria. When lava flows occur, the outer layer can solidify, while molten rock continues to flow beneath it. Once the eruption ends and the molten material drains away, a hollow tunnel remains. On Earth, these are called lava tubes, and they can be large enough to walk through or even drive vehicles through. On the moon, where gravity is weaker and there's no water erosion or tectonic disruption, such tubes could be vastly larger and better preserved. Evidence for lunar lava tubes comes from orbital imagery, showing skylights, round holes with vertical walls that appear to open into subsurface voids. These features don't match typical impact craters and often occur within ancient lava plains, suggesting collapsed ceilings of underground passages. Gravity measurements and surface collapse patterns imply that some tubes could exceed a kilometer in width. Such spaces would be invaluable for future human settlements. Shielded by meters of rock, habitats inside lava tubes would be naturally protected from radiation, micrometeorite impacts, and the moon's extreme temperature swings. Instead of building bulky shelters on the surface, astronauts could adapt these ancient tunnels into pressurized bases, laboratories, and storage facilities. Beyond their practical use, lava tubes represent untouched geological archives. Sealed off for billions of years, their interiors could preserve pristine samples of volcanic rock, trapped gases, or even water ice, offering a direct glimpse into the moon's fiery youth. Scientists envision robotic missions that could lower sensors or rovers into these skylights, mapping cavern systems that have never seen sunlight. Exploring such tunnels would be like stepping into a natural museum of lunar history, where the walls record an era long before Earth's continents or life emerged. The discovery of intact lava tubes would not only transform our understanding of the moon, but also reshape how we plan permanent outposts beyond Earth. Not all of the moon's mysteries are hidden under rock. Some play out in fleeting glimmers of light. For centuries, astronomers have reported seeing transient lunar phenomena, TLPs, brief flashes, glows, or color changes appearing on or near the lunar surface. Even before spacecraft exploration, these events were documented through telescopes, often clustered around certain craters like Aristarchus or Plato. With the Apollo missions, astronauts themselves saw similar flashes while orbiting the moon, confirming that at least some of these events were real and not just optical illusions caused by Earth's atmosphere. What causes these bursts of light remains uncertain. Several leading theories compete for attention. One is gas release. Micrometeoroid impacts, or slow geological shifts, may free trapped gases from the lunar crust, and under certain conditions, these gases could glow or scatter sunlight differently, producing momentary bright spots. Another is electrostatic activity. The moon's surface dust becomes electrically charged by solar radiation and can levitate or discharge suddenly when conditions shift, like static electricity sparking off a carpet. A third explanation involves meteoroid impacts themselves. High-speed collisions that create momentary flashes visible from Earth. NASA has even recorded such impacts with dedicated telescopes, especially during meteor showers, showing that the moon's surface is continually peppered by space debris. Despite decades of observation, TLPs remain unpredictable, which is why modern astronomers are installing automated telescopes to monitor the moon night after night. Some have captured dozens of candidate flashes in recent years, but sorting out which are genuine lunar phenomena and which are observational artifacts is an ongoing challenge. If future lunar bases are located near regions with frequent TLP activity, astronauts may finally witness these events up close, collecting the data needed to understand what's happening beneath the surface. Until then, TLPs serve as a subtle reminder that even in apparent stillness, the moon may be more dynamic and alive than it looks. Beyond seismic activity and transient flashes, the moon also exerts a subtler but profound influence on life here on Earth. Its gravitational pull drives the tides, the most visible manifestation of the moon's power over our planet. Twice a day, ocean waters bulge and retreat in a rhythm that has persisted for billions of years. This isn't just a coastal phenomenon. It's an environmental force that shapes entire ecosystems. Many marine species time their spawning, feeding, and migration to the lunar cycle. The Grunion fish of the Pacific beaches emerge from the sea during new and full moons to lay their eggs in the sand. Corals in the Great Barrier Reef release their reproductive cells in a spectacular annual event, precisely synchronized to the full moon. Even on land, animals respond to the moon. Lions hunt more successfully under darker moon phases, wolves adjust their howls and territories, and migratory birds use lunar cues to navigate. Insects, rodents, and even plants show subtle changes in activity tied to the lunar cycle. The moon is, in essence, a biological metronome, its light and gravity weaving through evolutionary time to imprint cycles on living organisms. Humans are not exempt from these influences. Folklore about full moons and madness has ancient roots, and although large-scale studies often find only minor correlations between lunar phases and human behavior, some research hints at measurable effects on sleep quality, hormone levels, and mood. For example, controlled experiments have shown participants taking longer to fall asleep and experiencing reduced deep sleep during full moons, even when they can't see the moon or know its phase. All of this suggests that while the moon doesn't cast spells, it does act as a subtle environmental force. Light levels at night during full moons historically shaped human activity, allowing longer hunting hours or social gatherings. Gravitational shifts may subtly influence biological processes we still don't fully understand. The moon's role as a timekeeper predates human culture, but its imprint is still detectable in our bodies and behaviors today. In this way, the moon serves as both a celestial partner and a silent architect of life's rhythms on Earth. For decades, the moon was thought to be utterly dry, a world baked by sunlight and stripped of anything as delicate as water. Early Apollo samples seemed to confirm this. No measurable moisture, no trace of ice. Yet later, analyses with improved technology overturned that assumption. Tiny volcanic glass beads brought back by astronauts were found to contain molecular water, implying that the moon's interior once harbored water-rich magma. This finding radically changed our understanding of the moon's history, suggesting it wasn't always as parched as we believed. In 2009, NASA's L-Cross mission delivered a dramatic confirmation. By crashing a probe into a permanently shadowed crater near the moon's south pole, scientists created a plume of debris that spectrometers quickly analyzed. The results showed unmistakable evidence of water ice mixed with lunar soil. These cold traps at the poles, places where sunlight never reaches, can preserve ice for billions of years at temperatures below 200 degrees Celsius. Estimates now suggest hundreds of millions of tons of water ice may be locked in these craters, an extraordinary resource for future exploration. Even more surprising is the discovery of hydroxyl molecules and trace amounts of water spread across the moon's sunlit surface. This water exists not as puddles, but as molecules bound within minerals or hidden inside microscopic voids in the regolith. It may migrate over the lunar day, sublimating during heat and recondensing at night, forming a kind of slow, invisible water cycle. Together, these findings depict a moon with a far more complex and dynamic surface chemistry than previously imagined, and they offer a tantalizing prospect: the resources necessary for sustaining human presence beyond Earth. Water on the moon is not just a scientific curiosity, it's a potential game changer for space exploration. Any long-term human presence on the moon will depend on access to local resources. Launching water from Earth is prohibitively expensive, but harvesting it in situ could support life support systems, agriculture, and even rocket fuel production through electrolysis into hydrogen and oxygen. This is why NASA's Artemis program and international partners are focusing their attention on the lunar South Pole, where permanently shadowed craters hold ice deposits shielded from the sun for billions of years. Mining and using lunar water, however, will be far from simple. Ice is mixed with regolith and buried in rugged terrain with no sunlight and extreme cold. Extracting it will require specialized drills, heating elements, or chemical processes to release and purify it. Even the hydroxyl-bound water on sunlit terrain would need to be baked out of minerals at high temperatures. Nonetheless, the moon's water is a stepping stone to deeper space. By learning to use it, we practice living off-world, reducing dependence on Earth and paving the way for missions to Mars and beyond. Beyond practical considerations, water reshapes our view of the moon as a planetary body. It hints at hidden reservoirs deep below the surface, at a more complex geological history, and at interactions with comets, solar wind, and Earth itself. In this sense, water is not just a resource, but a narrative thread connecting the moon's past, present, and future. It transforms our nearest celestial neighbor from a static gray sphere into a living laboratory of planetary processes, one that could hold the key to our expansion into the solar system. As we uncover more evidence of water and complex chemistry, our picture of the moon as a static, silent body continues to erode. We now see a world with volatile interactions, subtle geological stirrings, and a rich archive of early solar system history. Yet many of the moon's oddities go beyond what we can easily categorize. Take, for example, its uncanny orbital geometry. The moon spins on its axis once every 27.3 days and orbits Earth in the same time period, which is why we always see the same face. This synchronous rotation is not unusual by itself. Tidal locking is common throughout the solar system. But combined with the moon's large relative size and its precise distance from Earth, it produces perfect total solar eclipses. This cosmic coincidence is unique among known planets and moons. The Sun is roughly 400 times larger than the Moon, but also roughly 400 times farther away, making both appear almost exactly the same size in our sky. This alignment enables eclipses so precise and dramatic that they've inspired myths, religions, and scientific revolutions. Millions of years ago, the moon was closer and appeared larger, producing longer eclipses. Millions of years from now, it will be farther and too small to cover the sun completely, meaning total solar eclipses will vanish from Earth entirely. We're living in a narrow cosmic window when this alignment happens to be perfect, a fleeting circumstance on astronomical timescales. Some see this as pure chance. Others wonder whether it hints at deeper principles or unknown patterns in the evolution of planetary systems. Regardless of interpretation, the effect is real. The moon's distance from Earth is increasing by about 3.8 centimeters per year, altering the length of Earth's day in the process. This slow drift, driven by tidal friction, is one of the most subtle yet powerful forces shaping our planet's future, as well as our sense of time itself. The moon's gradual retreat from Earth tells a profound story about tidal friction and the interconnectedness of celestial mechanics. As Earth spins, its oceans bulge slightly ahead of the moon's orbit, dragging on our satellite and transferring energy to it. This causes the moon to spiral outward, while Earth's rotation slows down, lengthening our days. Today, each century adds roughly 1.7 milliseconds to the day length, a minuscule amount, but significant over geological time. Hundreds of millions of years ago, Earth's day lasted only 22 hours, and the moon hovered much closer, looming larger in the sky. If this process continues uninterrupted for billions of years, Earth and moon will eventually become mutually tidally locked, one side of Earth always facing the moon, just as one side of the moon always faces Earth. Days would lengthen to match the moon's orbital period of about 47 days, creating a world with an entirely new rhythm of daylight and darkness. In practice, the sun's eventual transformation into a red giant will intervene first, but the principle remains. The Earth-Moon system is evolving continuously, and the moon is a key driver of that evolution. Tidal friction has also stabilized Earth's axial tilt, keeping our seasons relatively steady. Without the moon, our planet's tilt might fluctuate chaotically, swinging from near zero to over 60 degrees, causing catastrophic climate shifts. In this way, the moon's presence has been a quiet guardian of Earth's habitability. It has slowed our rotation, moderated our seasons, and perhaps even made the emergence of complex life more likely. Understanding this dynamic isn't just an astronomical exercise. It's a way of seeing our own existence in context, a reminder that even something as basic as the length of a day is shaped by cosmic relationships far beyond our control. While the moon's orbital dance with Earth shapes time and tides, it also reveals a surprising degree of planetary interdependence. Earth's geography, its continents, ocean basins, and ice sheets, can subtly influence how tidal energy is transferred to the moon. As ocean currents shift and continents drift over millions of years, the rate at which the moon drifts away may accelerate or decelerate. Fossilized tidal patterns preserved in ancient rocks hint at such variations, suggesting that Earth and moon have been engaged in a dynamic feedback loop for billions of years. This makes the moon not just a passive satellite, but an active participant in Earth's geological and climatic story. Equally fascinating is the moon's role in stabilizing Earth's axial tilt. Our planet leans at about 23.5 degrees, creating the cycle of seasons. Without the moon's gravitational pull, that tilt might wobble chaotically over time, leading to extreme climate shifts. Computer models show that a moonless Earth could swing between near vertical and steep tilts of more than 60 degrees, causing catastrophic ice ages and tropical heat waves on unpredictable timescales. By contrast, the moon acts like a gyroscopic anchor, keeping Earth's tilt within a relatively narrow band. This stabilizing effect may have been essential for the evolution of complex life, ensuring a relatively stable climate over geological time. From another perspective, the Moon is also a time capsule of planetary evolution. Its ancient surface records bombardments and volcanic activity from the early solar system in a way Earth's ever-changing crust cannot. Even now, ongoing micrometeoroid impacts add a layer of new data, while seismic and electromagnetic phenomena hint at processes still unfolding inside. Each discovery, from water ice to rust to lava tubes, adds another layer to a portrait of the Moon as a dynamic system, one whose influence reaches far beyond its gray surface. Taken together, all these mysteries, the Moon's seismic ringing, its puzzling origin, its ancient rocks, its sodium tail, rust, water ice, lava tubes, transient flashes, and its subtle pull on Earth's life and time, paint a picture of our satellite as far more than a cold, lifeless rock. It is a partner in Earth's story, shaping our tides, stabilizing our climate, and offering a unique window into the earliest days of the solar system. The Moon stands as a reminder that even familiar celestial objects hold secrets deep enough to rewrite our understanding of the universe. As we prepare for the next era of exploration, missions like NASA's Artemis program, China's Chang'e landers, and private ventures may soon reveal even more hidden dimensions of our lunar neighbor. Future astronauts could descend into lava tubes, drill for ancient ice, or witness transient lunar phenomena firsthand. They may stand on the far side beneath radio-quiet skies, building observatories that look deeper into the cosmos than ever before. In doing so, humanity will not only return to the Moon, but also deepen our understanding of our own origins and future. For now, every glance at the Moon is a look into a cosmic mirror, reflecting both our past and our aspirations. It tells us that the universe is more complex, more interconnected, and more mysterious than we imagined. And it invites us to keep exploring, keep questioning, and keep reaching beyond our horizons. This is the promise and the power of our celestial companion. This is the journey we take together. Journey through time. Thanks you for joining this exploration of the Moon's deepest mysteries, and invites you to return for more stories that reveal the hidden connections between Earth, space, and time itself. Even beyond its influence on Earth and its hidden stores of ice, the Moon continues to challenge our assumptions about what a dead world should look like. One of the strangest revelations of recent decades is that the Moon may be shrinking. High-resolution images from NASA's Lunar Reconnaissance Orbiter have revealed thousands of small cliff-like features called lobat scarps. These scarps form when the crust contracts and breaks, pushing up ridges as the interior cools and solidifies. Some of these scarps cut across young craters, implying that the Moon has been geologically active far more recently than expected, perhaps within the last 50 million years. This contraction adds weight to the idea that shallow moonquakes detected by Apollo seismometers are connected to ongoing tectonic stress. The Moon, rather than being a static relic, may be slowly evolving even now, releasing seismic energy as it continues to cool. These processes reshape our understanding of the Moon's stability and have direct implications for building permanent bases. Structures located near active faults could be vulnerable to sudden jolts, while changing topography could complicate landing site selection. Future missions will need to map these scarps in detail and monitor them over time to understand whether they're still moving or simply fossilized traces of ancient shifts. If confirmed, a shrinking Moon becomes an extraordinary laboratory for studying planetary cooling and crustal evolution in real time. Unlike Earth, where plate tectonics and erosion obscure slow contraction, the Moon preserves its scars on the surface. By comparing seismic data with visible fault lines, scientists can test models of how rocky bodies lose heat over billions of years. This knowledge would also help interpret tectonic features on Mercury, Mars, and even distant exoplanets. In short, the Moon's subtle tectonic heartbeat may be our clearest window into the life cycles of rocky worlds. Another area where the Moon is rewriting expectations is its role as a cosmic archive of the solar system's most violent era. Earth's early surface has been erased by tectonics and erosion, but the Moon still bears the scars of a period known as the Late Heavy Bombardment, an epoch roughly 3.8 to 4.1 billion years ago, when asteroids and comets pummeled the inner solar system. The Moon's densely cratered highlands preserve a near-continuous record of that bombardment, offering clues about the migration of giant planets, the delivery of water and organics to Earth, and the conditions under which life first emerged. Each crater is a geological timestamp. By sampling its ejecta and dating its formation, scientists can reconstruct a timeline of impacts stretching back to the solar system's infancy. This makes the Moon an unparalleled testing ground for theories about planetary defense and asteroid impact dynamics. By comparing lunar craters with those on Mars, Mercury, and the moons of the outer planets, researchers can track how impact rates changed across space and time, refining our models of solar system evolution. Future robotic missions and human explorers could drill into these craters, extracting cores that reveal buried layers untouched for billions of years. Such studies would not only clarify the Moon's history, but also Earth's, since both bodies experienced the same barrage. We cannot dig 4 billion years into our own crust to find such evidence, but we can on the Moon. In that sense, every footprint we leave on its surface is also a step back through deep time, walking across the unaltered remnants of an era before continents, oceans, or even a stable atmosphere on Earth. The Moon's surface is more than a static record of impacts. It's also a laboratory for cosmic weathering. Without an atmosphere, the Moon is constantly bombarded by micrometeoroids, solar wind, and cosmic rays. This environment grinds and chemically alters the upper layers of soil, the lunar regolith, creating a dusty, electrically charged environment, unlike anything on Earth. Lunar dust is famously abrasive, clinging to spacesuits and equipment during Apollo missions, and causing problems for astronauts' eyes and lungs. Understanding the regolith isn't just a matter of keeping habitats clean. It's essential for every aspect of lunar engineering. Regolith grains are sharp-edged and coated with tiny glassy beads formed by micrometeorite impacts. They hold electrostatic charges that can make dust levitate or cling to surfaces. Future missions must design airlocks, filtration systems, and protective coatings to prevent dust contamination. But this same harsh environment also holds clues to processes occurring across the solar system. Solar wind implants hydrogen and helium into the upper few microns of soil particles. By studying these grains, scientists can measure the history of solar activity over billions of years. Data impossible to obtain on Earth, where the atmosphere shields us from direct solar bombardment. In addition, the Moon's lack of atmosphere means its surface records cosmic ray exposure continuously. Lunar soil effectively serves as a natural dosimeter, preserving a layered archive of radiation intensity. By drilling into regolith layers of different depths and ages, we could reconstruct a timeline of cosmic conditions stretching back to the birth of the solar system. This kind of information is invaluable for planning long-duration human missions to Mars or other planets, helping scientists predict radiation hazards beyond Earth's magnetic shield. The Moon's electrical environment also poses unique challenges and opportunities. Without an atmosphere to dissipate charges, the lunar surface can develop strong electric fields, especially at the boundary between sunlight and shadow. As the sun rises or sets over a given region, the sudden change in solar radiation can cause dust particles to become charged and lift off the ground, forming temporary dust fountains or halos near the horizon. Apollo astronauts reported seeing a faint glow above the lunar surface at sunrise and sunset, an effect now believed to be related to electrostatically lofted dust. This behavior has implications for both science and technology. For science, it reveals how charged particles interact in a vacuum, which can inform models of similar processes on asteroids, comets, and airless moons elsewhere. For technology, it means that solar panels, sensors, and mechanical parts on lunar bases may become coated or degraded by levitating dust. Engineers are already exploring electrostatic shielding systems and dust-repellent coatings to protect equipment. Some scientists even speculate about harnessing these charges for power, or using the phenomenon to transport fine materials across short distances. Understanding and mitigating the moon's electrostatic environment will be critical for sustainable operations. At the same time, it opens up a fascinating line of inquiry into the moon as a natural plasma laboratory, a place where sunlight, magnetic fields, and charged dust interact on scales we can observe directly. In this way, the moon becomes more than a destination. It's a testing ground for the physics of airless worlds, preparing us for exploration far beyond our own satellite. Beyond its physical and chemical mysteries, the moon also represents a cultural mirror, a body that has shaped human imagination, mythology, and science for millennia. From ancient Babylonian eclipse records to modern lunar landings, it has been both a clock and a canvas, guiding calendars, rituals, and navigation long before telescopes existed. Its regular phases provided humanity's first reliable measure of time, linking the sky to cycles of planting, migration, and storytelling. Even now, the moon's symbolism pervades art, literature, and popular culture, embodying mystery, transformation, and the allure of the unknown. Understanding the moon's science does not diminish its poetry. Rather, it deepens it. Each new discovery, water ice in shadowed craters, lava tubes stretching for miles, ancient zircons older than Earth itself, adds weight to our sense of awe. We now know the moon is not a static rock, but a dynamic participant in the evolution of the solar system. This dual role, as both scientific object and cultural touchstone, makes it unique among celestial bodies. No other world has been so deeply woven into human identity, while also serving as a laboratory for our future beyond Earth. Future exploration will likely amplify this connection. When humans establish permanent outposts on the moon, our cultural relationship to it will transform once again, from distant beacon to shared neighborhood. Stories of the moon will no longer be myths about a faraway place, but experiences of daily life under a different sky. This blending of science and story is part of what makes lunar exploration so compelling. It is as much about discovering ourselves as it is about discovering the moon. The moon also holds promise as a gateway to the solar system. Because it lacks a dense atmosphere and sits in a relatively shallow gravity, well compared to Earth, it could serve as a staging point for missions to Mars and beyond. Resources mined from the moon, particularly water ice, could be transformed into hydrogen and oxygen propellants, fueling spacecraft without the enormous cost of launching all supplies from Earth. Concepts such as lunar fuel depots, orbital transfer stations, and in-situ manufacturing facilities are being actively studied by space agencies and private companies alike. In addition, The moon offers ideal conditions for certain types of science impossible on Earth. The far side, shielded from terrestrial radio interference, is a prime location for building low-frequency radio telescopes that could probe the early universe. The stable environment and long lunar nights are excellent for infrared astronomy. Even seismic studies of the moon's interior can feed back into our understanding of Earth's formation and other rocky planets. In this way, the moon is not just a destination, but a platform, a natural base of operations for a species becoming interplanetary. Ultimately, the moon embodies the transition from exploration to settlement, from seeing to doing. Its proximity and familiarity make it the logical first step, but its mysteries ensure it will always be more than a stepping stone. By learning to live and work there, we will test the technologies, policies, and cultural adaptations needed for life beyond Earth. And in the process, we'll deepen our appreciation for the extraordinary cosmic partnership that has shaped our planet since its birth. Living and working on the moon will also teach us about closed-loop life support systems and psychological adaptation in ways no simulation on Earth can. Astronauts and scientists will have to develop methods to recycle air, water, and waste with near-perfect efficiency, using local resources wherever possible. This will require bioreactors, advanced filtration, and creative engineering to maintain an environment suitable for long-term habitation. Lessons learned on the moon can then be applied to Mars or deep space missions, where resupply from Earth is impractical. Another crucial dimension is human psychology. Life in low gravity, under an alien sky, and isolated from Earth for months at a time, will test our resilience, teamwork, and mental health. Early lunar crews will need to balance intense work schedules with recreation, communication with Earth, and personal space to prevent burnout. Cultural and interpersonal dynamics will also evolve. Just as seafaring communities once developed new traditions on long voyages, lunar settlers may develop rituals, symbols, or art forms unique to life on the moon. This sociocultural evolution will become part of the moon's living history, adding yet another layer to its role as a mirror of humanity. Establishing a permanent human presence on the moon may thus transform our species' self-concept. For the first time, home will not mean only Earth. The moon will become a second cradle, an extension of our biosphere, and a new stage for our stories. This profound shift in identity could be as significant as the advent of agriculture or the age of exploration, marking a turning point in our collective journey through time. As we plan for these futures, we must also confront the ethical and environmental implications of exploiting another world. The moon may seem barren, but it contains irreplaceable scientific and cultural heritage, historic landing sites, pristine craters, and geological formations untouched for billions of years. International agreements like the Outer Space Treaty provide a legal framework, but they are vague on specifics of resource extraction, heritage protection, and territorial claims. Developing fair, sustainable policies will be essential to avoid repeating Earth's history of competition and exploitation. There is also the question of how to balance science and commerce. Mining ice, building bases, and constructing telescopes will inevitably alter the lunar environment. Dust plumes from landings can travel hundreds of kilometers, potentially contaminating sensitive regions. Establishing planetary parks or protected zones, similar to national parks on Earth, has been proposed as a way to preserve key sites for future generations. Likewise, coordinating radio quiet zones on the far side is crucial for sensitive astronomical observations. Finally, The moon challenges us to think about our role as stewards beyond Earth. If we can approach lunar exploration with humility and foresight, we may create a new model for interacting with extraterrestrial environments, one based not on extraction alone, but on respect, reciprocity, and shared benefit. This ethical framework could then guide humanity's approach to Mars, asteroids, and beyond, ensuring that our expansion into the solar system enhances rather than diminishes our cosmic neighborhood. The moon also compels us to re-examine the very concept of ownership and governance beyond Earth. Because no nation can claim sovereignty over the moon under current international law, all activities there exist in a legal gray area. The 1967 Outer Space Treaty establishes space as the province of all humankind, but it does not clearly define how resources can be mined, sold, or shared. This ambiguity is now more pressing than ever as multiple countries and private entities prepare to extract water ice, rare minerals, and other valuable resources. Emerging frameworks like the Artemis Accords attempt to set voluntary standards for transparency, interoperability, and peaceful exploration. They include ideas such as safety zones around active operations and data sharing between signatories. Yet major spacefaring nations differ on how far these norms should go, and some have not signed on at all. Without broad agreement, future lunar development risks becoming a patchwork of competing claims and conflicts, undermining the moon's potential as a shared scientific and exploratory commons. At the same time, this uncertainty creates an opportunity to do things differently, to design governance structures based on equity and collaboration rather than competition. Some propose international consortia or public-private partnerships to manage lunar resources collectively. Others suggest a system of licensing or royalties that funds scientific research and infrastructure open to all. However it evolves, the governance of the moon will set precedents for how humanity treats other worlds, making it one of the most consequential policy experiments of the 21st century. Beyond legal and political questions, the moon also raises philosophical and existential ones. As we extend our presence outward, we are forced to confront what it means to be a multiplanetary species. Will we bring our terrestrial divisions and conflicts with us? Or will living under alien skies reshape our sense of identity and community? The moon, so close yet so profoundly different, is the perfect testing ground for this transformation. Already, artists, writers, and thinkers are imagining how lunar life might look. Cities carved into lava tubes, gardens under transparent domes, rituals timed to the 2-week day and 2-week night. Some envision a lunar culture emerging, one that blends Earth traditions with adaptations to low gravity and stark landscapes. Children born or raised on the moon could develop different physiologies, languages, or mythologies. Just as seafaring reshaped human society on Earth, spacefaring will reshape it again, and the moon is where it will begin. In this way, the moon is more than a scientific target or a stepping stone to Mars. It is a mirror for our future, reflecting not only what we have been, but what we might become. By studying its history, we glimpse our own origins. By settling it, we rehearse our destiny among the stars. Each new base, rover, and telescope will add to this unfolding story, a story not only of rock and dust, but of ideas, dreams, and the evolving human spirit. The moon's story also forces us to consider the long-term arc of human civilization. Every civilization on Earth has looked up at the same moon, yet each has interpreted it differently: goddess, god, clock, compass, or omen. Now, for the first time, we are poised to transform that archetype into a real-world domain of human activity. This represents more than a technological milestone. It is a psychological one. Our myths are about to become landscapes, our symbols, habitats. Such a shift compels us to examine how humanity adapts when confronted with entirely new environments. Lunar gravity, for example, is about 1/6 of Earth's, which will affect not just muscle and bone health, but also fluid distribution, plant growth, and material behavior. Architecture will evolve to suit these conditions, perhaps favoring vertical spaces, lightweight structures, or inflatable habitats. Agriculture will need closed cycles, artificial lighting, and careful nutrient management. Even art and sport could transform under reduced gravity, opening creative possibilities unimaginable on Earth. By designing for these conditions, we not only solve engineering problems, but also unleash cultural innovation. The moon could become a crucible of new human expressions, blending science, art, and survival into a novel way of life. Just as the Renaissance emerged from a confluence of factors, trade, technology, and rediscovery, so might a new Renaissance emerge on the moon, catalyzed by the meeting of planetary science, resource use, and human creativity under an alien sky. We must also think about how the moon fits into humanity's long-term presence in space. In the near future, lunar infrastructure, mines, refineries, habitats, and observatories could link with cislunar space stations and Earth-orbiting facilities. This network might form a greater Earth system, a cluster of habitats, transport routes, and communication relays spanning hundreds of thousands of kilometers. The moon would function as both a supply depot and a training ground, bridging the gap between our home planet and deeper destinations like Mars, the asteroid belt, or even the moons of the outer planets. Such a network would dramatically alter our economy, science, and culture. By reducing the cost of launching from Earth, we could accelerate space-based solar power, asteroid mining, and interplanetary exploration. The moon's stable surface and far side provide unmatched platforms for telescopes to peer into cosmic dawn, gravitational wave detectors to probe black holes, and particle experiments to study fundamental physics without earthly interference. In time, the moon might even host data vaults, or archives designed to preserve human knowledge against terrestrial disasters. A cosmic library, etched into regolith, or stored deep inside lava tubes. All of these possibilities depend on the choices we make now. Will we treat the moon as a partner or a quarry? Will we create inclusive governance or repeat the mistakes of colonization? The answers will shape not only our lunar future, but also our expansion across the solar system. In this sense, the moon is less an endpoint than a mirror of our values, magnifying both our ingenuity and our responsibilities. Another dimension of the moon's importance lies in its potential as a scientific time machine. Because the moon lacks atmosphere, weather, and plate tectonics, it preserves not only its own history, but also traces of Earth and the wider solar system. Micrometeorites striking the lunar surface may have delivered fragments of Earth's early crust, blasted into space by asteroid impacts billions of years ago. These Earth meteorites, embedded in lunar regolith, could hold the only surviving samples of prebiotic Earth, minerals, organics, or isotopic signatures from an era otherwise erased from our planet's surface. This possibility excites astrobiologists. If Earth life emerged early, then fragments of early microbial ecosystems may have been ejected into space and landed on the moon, frozen in time. Drilling into ancient regolith layers could reveal clues to the origin of life, the composition of Earth's primordial oceans, or the conditions under which biology first flourished. Such discoveries would revolutionize our understanding of life's beginnings and inform the search for life elsewhere. The moon could also preserve records of supernovae, gamma-ray bursts, and cosmic ray intensity over billions of years. By studying isotopic anomalies in lunar soils, we could reconstruct the Milky Way's past events, mapping how our galactic neighborhood has changed over deep time. In this sense, the moon is more than a satellite. It's a witness, a silent archivist of cosmic history, holding pages of a book Earth can no longer read. Finally, the moon is a reminder of how exploration transforms explorers. Every Apollo astronaut who set foot on the moon returned profoundly changed, describing a new awareness called the overview effect. A cognitive shift in seeing Earth as a fragile, interconnected whole, suspended in darkness. From the lunar surface, national borders vanish, and the planet appears as a single shimmering oasis. This perspective can inspire a sense of stewardship, empathy, and humility, difficult to achieve from within Earth's boundaries. As future astronauts, scientists, and even tourists travel to the moon, this transformative experience could spread more widely, reshaping how humanity thinks about itself. Standing under a black sky dotted with stars, with Earth a glowing marble on the horizon, may produce new philosophies, art, and policies grounded in planetary consciousness. Just as the first photographs of Earth from space sparked the environmental movement, mass exposure to the overview effect could catalyze new global priorities, from climate action to conflict resolution. In the end, the moon is more than an object of study. It's a stage on which humanity rehearses its cosmic role. Each rocket launched, each footprint placed, each experiment conducted, writes another line in a story as old as starlight and as new as tomorrow's launch schedule. By exploring the moon, we're not only learning about a celestial neighbor, but also about ourselves, our ingenuity, our limitations, our hopes. And that story, still unfolding, invites everyone to look up, wonder, and imagine what comes next. As we imagine the future of lunar exploration, it is important to recognize that the moon also represents a unique training ground for planetary defense. Because it has no atmosphere, every meteoroid that strikes the moon leaves a mark, and these impacts happen constantly at all scales. By monitoring fresh impact flashes and studying new craters with high-resolution imaging, scientists can refine models of how frequently space debris hits planetary surfaces. This data helps us assess risks to satellites, space stations, and even Earth itself. Robotic networks on the moon could serve as an early warning system, detecting and characterizing meteoroid streams before they intersect Earth's orbit. Instruments placed in stable lunar locations could also improve our understanding of near-Earth asteroids, gravitational perturbations, and the long-term behavior of potentially hazardous objects. In this way, the moon becomes a sentinel as well as a sanctuary, our outpost for looking outward as well as inward. At the same time, the moon's environment, vacuum, microgravity, temperature extremes, offers the perfect conditions to test materials, electronics, and life support systems destined for Mars or deep space. Engineers can run long-duration trials with minimal risk of contaminating Earth's biosphere. Over time, a lunar industrial base could produce propellant, spare parts, and even entire spacecraft, turning the moon into a launch pad for the rest of the solar system. The moon's vast plains and rugged highlands also offer unparalleled opportunities for geological fieldwork at planetary scale. Unlike Earth, where erosion and vegetation obscure ancient formations, the moon's surface is like an open-air museum of planetary processes frozen in time. Astronauts trained as geologists could traverse lava flows billions of years old, collect impact melt from giant basins, and map the layering of ejecta blankets to reconstruct the chronology of bombardments. Each sample returned could refine the lunar timescale and, by extension, the timeline for all inner solar system bodies. This fieldwork would also deepen our grasp of comparative planetology. By understanding the Moon's crust, mantle, and core, we improve our models for Mercury, Mars, and exoplanets of similar size and composition. Lava tubes on the Moon could reveal how volcanic plumbing systems evolve in low gravity, while polar ice layers could show how water migrates across airless worlds. Even subtle phenomena such as dust charging, seismic attenuation, and tectonic scarps provide analogs for distant worlds we can't yet reach. In essence, the Moon is our nearest laboratory for understanding the universe. Every rover wheelprint and astronaut bootprint can be seen as an experiment in how humans and technology adapt to a new world. Each crater, boulder, and mineral grain offers a clue to cosmic history. By continuing to explore it systematically, we are not merely preparing for future missions, but also rewriting textbooks, transforming a once mysterious orb into the key to a much larger cosmic puzzle. Beyond its physical and scientific importance, the Moon may also play a role in reshaping human collaboration on Earth. Because no single nation can own the Moon, international partnerships are not just desirable, but necessary. The International Space Station has already shown how multiple countries can cooperate in orbit. The Moon will test whether that spirit of collaboration can extend farther, across different political systems and economic models. Joint missions could reduce costs, share risks, and increase scientific returns, creating a more inclusive approach to space exploration. This cooperative framework could also accelerate technological innovation. By standardizing docking ports, communication protocols, and habitat modules, international partners can ensure interoperability and flexibility. Lunar supply chains might resemble today's global trade routes, but with spacecraft and robotic ferries instead of cargo ships. Such networks could encourage the participation of emerging spacefaring nations, universities, and even citizen scientists, democratizing access to lunar research and resource use. Culturally, a multinational lunar presence might produce a shared identity, an Earth team working on the Moon. This could help transcend national rivalries and provide a new narrative for humanity as a single species venturing outward together. In an era of global challenges, climate change, resource scarcity, geopolitical tension, the Moon could become a stage where cooperation, rather than competition, defines our next chapter. Finally, the Moon embodies a continuum between past, present, and future. It began as part of Earth or as a close sibling in the early solar system. It shaped our tides, our timekeeping, and perhaps our evolution. Today, it draws our spacecraft, our dreams, and our ambitions. Tomorrow, it may host our laboratories, factories, and communities. Through it all, it remains the same glowing orb in the night sky, connecting countless generations. In this way, every new discovery about the Moon reflects back on us. When we find water ice, we're also finding a path to sustainability. When we map its fault lines, we're learning about planetary cooling and tectonics. When we drill into ancient regolith, we're touching the earliest pages of our solar system's story. The Moon is not only a destination, but also a lens, magnifying our curiosity, refracting our values, and focusing our will to explore. The journey to understand the Moon will never be finished. As instruments grow more sensitive and missions more daring, each answer will open new questions. Yet this is precisely why the Moon matters so deeply. It offers both a grounding point and a launch point, solid enough to stand on, mysterious enough to inspire. In the endless interplay between known and unknown, the moon is our nearest reminder that the universe still holds wonders waiting to be uncovered. One of the most underappreciated aspects of the moon is its potential to preserve humanity's legacy. Because the lunar surface is so stable, it can serve as a kind of cosmic vault for knowledge, culture, and even biological material. Concepts like the lunar library envision storing vast amounts of human data, books, art, DNA, and scientific archives, etched onto durable media and buried deep in lava tubes or regolith to last millions of years. Unlike Earth, where erosion, war, and natural disasters can destroy archives, the moon offers a relatively unchanging environment. Such repositories could act as a safeguard for civilization. If catastrophic events struck Earth, future generations, or even visiting extraterrestrials, could recover humanity's history from these lunar archives. This is not merely science fiction. Prototypes of such data vaults have already been flown on missions to the moon. In effect, the moon could become humanity's ultimate backup drive, a silent guardian of our collective memory, orbiting just 3 days away. Beyond data, the moon could also host seed banks, cryogenic samples, and even experimental biosphere modules containing microorganisms or small ecosystems. These could test our ability to preserve and restart life in off-world environments. Such projects raise deep ethical questions, but also extend our notion of stewardship, shifting from preserving life on one planet to safeguarding it across multiple worlds. The moon also provides a rare opportunity to practice sustainability from the ground up. On Earth, industrialization evolved incrementally over centuries, often without regard for long-term environmental impacts. On the moon, we have the chance to design an entire economy and infrastructure from first principles, incorporating closed loops, minimal waste, and renewable energy from the outset. Solar power is abundant during the 2-week lunar day, and permanently shadowed craters could be used for cryogenic storage or dark sky observatories. By treating lunar resources as finite and precious, we can model an economy that prioritizes reuse and efficiency. This approach could influence our behavior back on Earth. Technologies developed to survive and thrive in the moon's harsh environment, water recycling, waste minimization, dust management, could have immediate applications in arid regions, disaster zones, or closed habitats on our home planet. In this way, the moon becomes a proving ground, not just for interplanetary living, but for more sustainable living everywhere. Moreover, the moon challenges us to measure progress, not solely in extraction or expansion, but in knowledge and stewardship. Each mission can be planned with explicit goals for minimizing disturbance, documenting changes, and leaving sites in a condition useful for future research. If we succeed, the moon may become the first example in human history of a large-scale frontier developed with foresight and responsibility, a legacy that could echo across the solar system. Another underexplored dimension of the moon is its role as a platform for education and public engagement. Because it is visible from every populated region on Earth, the moon offers a uniquely accessible target for global science programs. Schools and citizen scientists can observe its phases, track its features, and even contribute to mapping projects coordinated with space agencies. As robotic missions increase, live data streams from lunar rovers could allow classrooms to virtually drive across the moon's surface, fostering hands-on STEM education for millions of students. This public connection can shape policy and funding. Apollo's televised moments captured global imagination, and future missions could do the same, especially if they incorporate interactive elements. Imagine a mooncam network, transmitting high-resolution images 24/7, or public votes on where to send the next rover. Such initiatives not only democratize exploration, but also build a shared sense of ownership and responsibility. In this way, the moon becomes not just a scientific object, but a classroom for humanity, inspiring the next generation of explorers and innovators. Moreover, cultural exchanges tied to lunar exploration, art, music, storytelling, can build bridges across borders. Just as the Earthrise photo united a planet in awe, future lunar milestones may generate moments of collective wonder, reinforcing our shared identity as Earth dwellers under one sky. The moon also challenges us to consider long timescales, far beyond a human lifespan. While political cycles and business plans run in years or decades, lunar processes unfold over millennia or even billions of years. Planning infrastructure on the moon means thinking about structures that could endure for centuries, weathering micrometeoroids, radiation, and temperature extremes. This perspective forces engineers, scientists, and policymakers to adopt a kind of intergenerational thinking rare on Earth. Such thinking has powerful benefits. If we design lunar settlements, archives, and observatories with longevity in mind, we create models for sustainable development at home. By imagining habitats that can function autonomously for decades, or telescopes that can operate through multiple human lifetimes, we anchor our ambitions in durability rather than disposability. This shift in mindset could influence everything from architecture to resource management to education, preparing society for challenges that unfold on planetary timescales. Ultimately, the moon invites us to redefine progress. Instead of measuring success by how fast we extract resources or how quickly we plant flags, we could measure it by how well we preserve, learn, and pass on. Each base, drill core, or instrument left behind could become part of a permanent human and scientific heritage, available to those who come after us. This is the moon's quiet lesson: to think bigger, longer, and more responsibly than we ever have before. The moon is also emerging as a test bed for autonomy and artificial intelligence. Because it is only a few days away, it allows engineers to test advanced robotics, autonomous vehicles, and AI-driven habitat management under true off-world conditions, but with relatively quick communication loops. Rovers operating on the lunar far side or inside lava tubes will need to navigate without constant input from Earth, relying on machine vision, local mapping, and adaptive algorithms. These technologies can later be scaled for Mars, asteroids, or deep space missions, where communication delays are far greater. Additionally, the moon offers a perfect proving ground for swarm robotics. Fleets of small, inexpensive rovers or drones that can coordinate to map terrain, build infrastructure, or transport materials. Such systems could assemble solar arrays, deploy communication relays, or even construct habitats using in-situ resources. By refining AI and swarm coordination in the lunar environment, we accelerate the development of resilient, distributed systems capable of handling the unexpected in harsh environments. These advances will also spill back to Earth. Algorithms designed to manage life support, energy distribution, and resource extraction in real time on the moon could improve smart grids, disaster response, and automated construction at home. Thus, the moon's harsh conditions drive innovation, not just for space, but for society at large. The moon's unique environment also positions it as a laboratory for fundamental physics. In the radio silence of the far side, scientists could build ultra-sensitive antennas to detect faint cosmic signals from the early universe. signals that are blocked by Earth's ionosphere. Gravitational wave observatories on the Moon could measure ripples in spacetime with far greater precision than Earth-based detectors, benefiting from low seismic noise and stable ground. Neutrino detectors buried deep in regolith or lava tubes could search for elusive particles that pass through entire planets undetected. Furthermore, the Moon's stable surface and low temperatures make it ideal for long baseline interferometry, linking multiple telescopes to create planet-sized observatories. Such facilities could image exoplanets directly, map cosmic magnetic fields, or test theories of dark matter and dark energy. By turning the Moon into a science park for the universe's deepest questions, humanity gains an unparalleled vantage point on the cosmos. These possibilities transform our nearest neighbor into a cornerstone of discovery. Just as Antarctica became an international hub for climate and astronomy research, the Moon could become a neutral cooperative zone for physics and planetary science, a place where nations work together to unlock the secrets of reality itself. As our journey across the Moon's mysteries draws to a close, we return to where we began, looking up at that familiar yet forever enigmatic sphere in the sky. Over these many chapters, we have explored seismic echoes that linger like cosmic bells, origins lost in ancient collisions, ice locked in eternal shadow, tunnels carved by fire, sparks of transient light, and a gravitational pull that shapes life itself. We have seen the Moon not as a static rock, but as a living archive, a training ground, a mirror of our past, and a compass for our future. Every discovery on the Moon reflects something about ourselves, our curiosity, our capacity for collaboration, our hunger to reach beyond horizons. Each crater, mineral grain, and beam of light on the Moon becomes a clue not only to its story, but to the story of Earth and the solar system. And as we prepare to return and stay, we are reminded that exploration is not just about moving outward, but also about looking inward, understanding who we are, what we value, and how we will live on other worlds. Thank you for traveling with us through this extraordinary exploration. May the Moon continue to inspire questions, dreams, and new frontiers for generations to come. This has been Journey Through Time, inviting you to keep looking up, keep wondering, and keep joining us as we uncover the hidden stories of our universe.